Hello, welcome to your lesson on transforming trigonometric functions. As you may remember, transformations are things we do to mathematically change equations and resulting in functions when graphed that change. They either move or they get dilated, compressed, or expanded, or perhaps even reflected. Let's get rolling. Okay, so transforming functions. Let's begin with something like this. We know this is a basic exponential graph. That was a topic of our last unit. Now, if we took that one and rewrote it like this, we have all these new parameters here. We have a here in front, we have a c there with the x, we have a d at the end. As you may remember, each of those numbers we introduced there has an effect on what the graph looks like. So let's take a look. A basic exponential graph, 2 to the x power, is shown in red. All right, there's a basic exponential growth graph. We can see, let's see, yeah, exponential growth. And there's an asymptote, as you may remember, at y equals 0. But now look at the blue one. The blue one is one where I've introduced all these parameters, right? There's all these things. I've introduced numbers there. I put a 3 in front here, I put a 5 up there multiplying with the x, and I put a 7 at the end. And notice the graph has changed. It has been transformed. It has been moved. It has been compressed. All these things have happened at once. One of the main numbers we looked at here that was most important was the number at the end. When we have a number at the end that we're adding here, it shifts the graph vertically. In other words, up and down. So notice the red one to become the blue one, it moved up. And we see a plus 7 here, so it went up 7 units. So whereas the asymptote used to be down here at the axis, the asymptote is now here at y equals 7. And that was important. We looked at that when we were looking at the cooling liquid graphs, and we had a certain asymptote, like at room temperature. That's the same idea there. This changes the asymptote. Okay, so that's the idea of transforming functions. Let's apply that to what we learned about sine and cosine waves the other day. So we did graph these the other day. The green one here is a sine curve. It begins at 0, goes up to 1, then down to -1, and back again, and then repeats forever. The purple one is a cosine graph. And we talked about this. Cosine and sine graphs have exactly the same shape, except for one is a shifted version of the other. If you move one left or the other one right, you can have them overlap perfectly. So cosine graph, the normal one in purple here, cosine, begins at 1, goes down to -1, and then comes up again. So those are our graphs. So what happens if we transform those? So here's a regular sine graph. And what would happen if we introduced all these parameters? So again, if we put a number in front, if we put a number there with the x, and if we put a number at the end. So maybe this already looks familiar based on what we were talking about with the exponential graph a moment ago. But we're going to take a look in this lesson about what each of those parameters does to the graph. And likewise, we have a basic cosine graph. We're going to do the same thing. Introduce the same parameters and see how it affects it. Well, I think you're already thinking those parameters in the sine graph will have the same effect as they do in the cosine graph. And that's absolutely right. They will have the same effect. So let's take a look at what those parameters do. Okay, first things we're going to look at is something called the principal axis and the amplitude. So the principal axis can be found with this little formula here. But I often tell you, let's not memorize formulas. If we just understand concepts, we don't need formulas. But we'll try this formula and then we'll discuss what it means in terms of the graph. But basically, to find what's called the principal axis, we do the max point plus the min point divided by 2. And the second thing we're going to look at is the amplitude. Looks very similar to the formula, but now we're doing max minus min divided by 2. So let me show you what those mean. Again, here's our basic sine curve, sine x. Okay, begins at 0, goes up to 1, goes down to -1, comes back to 0. There's a sine wave. Alright, so let's find the principal axis. The formula tells us we're going to take the maximum point, which on this graph the maximum point is 1. And the minimum point is -1. So we're going to take 1 plus -1, max plus min, 1 plus -1, and divide it by 2. It's always divided by 2. Okay, so it's kind of like saying we're finding the average. And you might recognize that. Yeah, when you add two numbers and you divide by 2, that's finding the average. And that's what we're doing. The principal axis is the average. It's saying what's exactly in the middle of the max and the min. So if the max is here and the min here, what's the middle of that? Well, 1 plus negative 1 is 0, so we get 0 over 2, which is just 0. So what we have is the principal axis, and it basically is the midline, All right, we have found it by taking the average between the max and the min, so we found something right in the middle between the max and min. It is our middle line on the sine or cosine curve. Okay, so that's the principal axis. In this case, it has an equation of y equals 0. Okay, how about the amplitude? Max minus min divided by 2. Okay, so max number 1 minus the min number, which is negative 1, so we have double negatives here, okay, divided by 2. Negative negative makes a positive, so we end up with 2 divided by 2, which is 1. Okay, what does the amplitude represent? Let's take a look. So the amplitude is just the height of the wave from the midline, okay, from the midline. So there's an amplitude of 1 there, and we can see here also from the midline to that point, that's also 1. So that's the amplitude, 1, 1, okay? Amplitude happens to be half the distance from top to bottom, right? And that's what we're doing here. We're finding the distance from top to bottom. That's what this subtraction is doing. And then dividing by 2, because we need half of it to find the amplitude. All right, that's on the basic curve. Now let's look at a transformed curve. I have this function here, 3 sine x plus 1. So I've graphed another sine graph. It has changed because of these two parameters here. Let's find the principal axis and the amplitude. So use this formula for principal axis and find it for this one. Okay, here we go. Max plus min. Maximum point in this case is 4, minimum point is negative 2, I can see. So we add those and divide by 2. 4 plus negative 2 is 2, divided by 2 is 1. So the principal axis should be at y equals 1. Well, there's the line y equals 1, horizontal line. Does that make sense as the middle line of this? Well, there's only one way to find out. If this is the middle line, it must be equally distant from the max point and the min point. So what's this distance here? From 1 to 4. Okay, that's a distance of 3. How about this one? From 1 down to negative 2. Oh, that has a distance of 3 also. So this is definitely the midline. We found the midline. And remember, it's like finding the average, and that's what we're doing here. Okay, now let's find the amplitude. So calculate the amplitude using this little formula. Okie dokie, we have 4 minus negative 2. Max minus the min. That turns out to be 6 over 2, which is 3. That tells us the amplitude. And again, the amplitude is the height. And even without that formula, we were just talking about the amplitude a moment ago. We had the midline, and then we just check from the midline to the top. Oh, that's 3 units. From the midline to the bottom, 3 units. So we don't really need the formula. It helps us, sure, but we can just see the distance clearly on here. Okay, so that's principal axis and amplitude. Pause if you need to take another look at that. Okay, let's move on. Let's talk about something called the period. The period is basically how long it takes to complete one wave. So let's take a look here. Here's our midline again. Here's our amplitude. Here's our amplitude. And then from here, okay, this is where the wave begins. And if I follow the wave, it comes back to that same starting place. That's a full wave. That is your period, okay? So if for a normal sine curve, we talked about that last time. The period is 360 degrees. Okay, that's the normal sine curve. Let's say we have a different one here. Wow, I have a completely transformed one. 2 sine 3x minus 1. Okay, what's going on? Look at the period here now. Well, first of all, here's the midline. Did you calculate? Yeah, hopefully calculate that. And then what's the amplitude? Okay, so the amplitude is 2 units. Midline was at y equals negative 1. Okay, and now what is the period? This is important. Check it out. I'm going to start the wave right here. Started, there, ends right here. So started there, ended there. That's one full wave. That's our period. So how many degrees is that? 120 degrees. So now notice in the normal 360, see, normally it takes 360 to complete a wave, but now in the normal 360, 1, 2, and 3 waves are completed. Now, do you see a 3 in here somewhere? Yes, right here. So guess what? That number there is what's called a frequency. And frequency tells us how many waves occur in the normal, I guess, in the normal zone of one wave. The normal zone is 360, and this tells us, okay, now 3 waves will occur in there. And therefore, if 3 waves occur in there, then each wave only has a period of 120, because it's 1/3 of the whole 360. Okay, anyway, that's some important things there to know. So your period there is 120. Okay, so if we had this function, this is with the parameters introduced, and it's kind of like the one we see here. I want you to tell me, what does the A represent? What does the A represent on the graph? Take a close look. Okay, A is the amplitude. That value in front tells us the amplitude. Here we had an amplitude of 2, and that value we can see is there. Okay, how about D, this last number here? What does that determine on the graph? Alright, I hope you're looking at it and saying, hey, that's the vertical shift. The normal sine graph has a middle line at y equals 0, but now it's at y equals -1. The whole graph shifted down 1. That number here, -1, tells us how much is shifted up and down. And that's exactly like we saw for the exponential curves, where we had this shift based on that number, vertical shift. Okay, now finally, what is B? Okay, and I just talked about B. B is what's called the frequency. And frequency tells us our period. To get the period, we take 360, the normal period, divided by the frequency. So in our case, we say, hey, the normal period is 360. I'm going to divide by the frequency value, this 3. 360 divided by 3 tells me my period, 120. That's the little formula for period right here. Okay, see if you can fill in this table. Based on what we just learned, what should go in these boxes here? What's the amplitude, period, and principal axis? Okay, I hope you saw 2, 360, and 0, 2. There's the amplitude number. We don't see a number in here, no frequency number, therefore normal period. And there's no number at the end, so it hasn't shifted up and down, so therefore principal axis remains at y equals 0. How about this one here? Okay, let's check. Alright, the only adjustment was this 3. And remember, that represents frequency. So now 3 waves occur in 360, therefore each wave has a period of only 120. Right, we take 360 and divide by that number to figure out the period. Okay, how about here? What's going on? Okay, same amplitude, same period, because we see the 3 there, and then now there's been a shift of 1 up, so the principal axis, that middle line, is at y equals 1. How about here? Okay, check your numbers here. Amplitude, normal period, y equals 0. How about here? Oh, a little tougher. Think about this one carefully. That was a 3 and it made it 120. So now this is actually a half, because this x divided by 2 means there's a half there. So that half means it does what to the period? Check it out. The period is 720, because here this means 3 waves occur in the regular 360. This means only half a wave occurs in the regular 360. So it takes 720 to complete a full wave if only half a wave is accomplished in 360. Great. And look at this one. What's the difference here? Okay, check the numbers there. That's 720. Now there's been a vertical shift. So the middle line is -3. Awesome. Let's look at that on decimals real quick. Okay, on decimals, I have it here. We have our regular sine graph. I'm going to show you when I change the A value. Look, the amplitude changes. Great, A changes the amplitude, gets higher and lower. Okay, D value. Alright, that's the one that at the end, right, the vertical shift. And see, it goes down, it goes up, vertical shift. And then the B value changes the frequency, how many waves fit. See, as I make the B value bigger, there's more waves in 360. As I make the B value smaller, there's fewer waves in 360. Awesome. Alright, let's do a couple more things. Look at this one, predict the amplitude, period, and principal axis. Okay, now check your work. Alright, and this one, predict the amplitude, period, and principal axis. A little bit tougher to see here. Check it out. Okay, and now check those things there. Okay, let's do an applied problem for you guys. Okay, this one here. Read the problem and try to find the amplitude. Okay, now check your work. Amplitude is 20, and it says justify. This is how we justify it. We use a little formula for amplitude, and we justify that it matches what we saw in the graph. Try B. Okay, the period, I can see one wave being completed in 120 here. Okay, let's justify that. Period is 360 over frequency, and we know in this case 360 over 3, we see that 3 number there, that's our frequency, so that justifies our period number. Try one more, try this one out. Okay, and now check your work carefully. There's the answer for that problem there. Great problem. It has you checking things out right here. Check your work carefully. It's a good one to study. Great job.